Hello everyone, I am Erfan Pourshaban, a doctoral student at the University of Utah. It is my pleasure to share my research results at the IEEE Sensors 2021 conference. Today, I will present my latest results regarding an electrolytic power scavenger which is activated by means of a natural eye blinking to supply power to smart contact lenses. I will first talk about the applications of the smart contact lenses. Different methods to supply power for smart contact lenses will be pointed out in the next slide. Then, I will explain why our new power generation strategy is superior to the previously reported techniques. In light of these, I will describe the working principle of our energy generator device together with the experimental setup to test the device. Finally, I will present our experimental results. Remote health monitoring, disease diagnosis, and curing lead to crucial advantages. It saves money and time by removing the commuting and time-consuming tests. Also, it can potentially save human beings' lives by giving them the opportunity to have more accurate control over their health parameters. Furthermore, it can help people to have easier life by real-time corrections and curing techniques. As it is shown in this slide, glucose detection, drug delivery, vision correction, and disease diagnosis are the most important applications of the smart contact lenses, which can help billions of people to have healthier and much easier life. However, the power supply to smart contact lenses is an obstacle toward its widespread adoption and commercialization. This slide shows several energy delivery methods for smart contact lenses, including photovoltaics, batteries, and wireless induction. Unfortunately, all of these techniques either suffer from environmental dependency or limited energy availability. For example, the photovoltaics require light to operate and stops working in dark conditions, or a radio scavenging delivers very low power and very low distance range. Therefore, it is vitally important to develop an environmentally independent and powerful technique to supply power to the microelectronics and optical elements on smart contact lenses. For the first time, we could be able to show that it is not only possible to take advantage of natural eye blinking for power generation, but also the generated power is one of the most powerful techniques ever reported. This slide shows the working principle for the electrolytic energy harvester. The generator consists of two polarizable electrodes, a hydrophobic surface, and eye tear as the electrolytic solution. When the liquid is not touching any of the electrodes, the device is in off mode. When the liquid is gradually covering the first electrode or the anode, the spontaneous electrochemical reactions take place, resulting in electrical charge generation. Finally, when the liquid touches the second electrode or the cathode, the charge transfer and the power generation occur. The interesting electrical outputs prompted us to introduce the power generation by means of natural eye blinking. As it is shown in the right figure, this device can be mounted on a smart contact lens. An adult blinks 10 to the 4 times a day, so the proper exploitation of the frequent back and forth blinking motion can deliver electrical power. When the eye is completely open, the device is in off mode. When the eyelid is gradually closing, the eye tear goes into contact with the anode and charge generation occurs. Subsequently, the power will be generated as soon as the eyelid gets fully closed. This slide shows the constructed device and the experimental setup. Different methods anodes, including aluminum, copper, nickel, and chromium, were deposited using a plasma sputtering machine. In addition, gold was deposited to serve as the cathode electrode. One micrometer side-top was deposited to make a hydrophobic surface between the electrodes. The side-top was photolithographically patterned and dry-etched to access the electrode. A linear actuator provides the eye-blinking sliding motion. We measure the voltage and current output of the capacitor while the device slides on a moisturizing eye tear. Furthermore, we have used a 4.7 microfarad capacitor as an energy storage unit to further testify the practical application of the novel energy harvester. Frequent back and forth sliding motion of the device on top of the moisturizing eye drop result in voltage and current pulses. The maximum voltage and current of 240 mV and 20 microamp were recorded while using copper as the anode. Replacing copper with aluminum resulted in a much greater electrical outputs of 700 mV and 48.8 microamp. Integration of the current time plot over one pulse shows the charge generation of 2.2 microcoulomb and 13.9 microcoulomb while using copper and aluminum as the anode respectively. We also charged a 4.7 microfarad capacitor by means of our motion-activated energy generation device. The power outputs are 0.26 and 1.53 microwatt. So with this, I want to conclude this presentation, and finally I would like to acknowledge the support of National Science Foundation under the Cyber Physical Systems program together with the University of Utah's NanoFab facilities. And finally, thank you very much for your kind attention, and I will be happy to answer your questions.